Okay, so good afternoon, everybody. My name is Timur Olsson. I'm one of the co-organizers together with Rocio Mercado of this Chalmers AI for Science seminar series, which is now part of the chair structured learning theme. So in this seminar series, we invite junior and sort of medium career researchers at the interface of AI, machine learning, and the natural sciences to present some of their work. And today we have the pleasure of introducing Rafael Gomez Bombarelli, who is the Jeffries Chi Chair Career Development Professor at MIT's Department of Material Science and Engineering. His work aims to fuse machine learning and atomistic simulation for designing materials and their transformations. By embedding domain expertise, experimental results into their modeling, along with physics-based knowledge, the Learning Matter Lab, which is the lab that Rafa leads, designs materials that can be realized in the lab and scaled to practical applications. Together with experimental collaborators, they develop new practical materials, such as heterogeneous thermal catalysts, such as zeolites, transition metal oxide catalysts, therapeutic peptides, organic electronics for displays, and electrolytes for batteries. Rafa has bachelor's, master's, and PhD from the University of Salamanca in Spain. And he has done a postdoc at Harvard and had a brief industry stint with in a startup company. And he's been awarded several prestigious prizes, including his work at the interface of machine learning and the chemical sciences. He's a Google research faculty. He got the Google Research Faculty Award. Yeah, so we're very happy to have you here today, Rafa, and please go ahead and take it away.
A pleasure. Thanks so much for the opportunity to chat. Like Simon mentioned in the pre-game, if anybody has questions, just feel free to stop me. I'll keep an eye on the chat if I can find it here. So if I look into the side, it's because I'm reading the chat. But thanks so much. Thanks so much for the intro. Today is mostly I'm going to try to sort of talk about sort of the method side of what we've been doing, maybe a little bit less focus on sort of the materials impacts. But I want to preface what we do and put it in context. And the context is a climate and sustainability crisis, right? We've built our whole lives and industries in a way that is not sustainable. And the climate change reports get dire and dire, more and more dire. And there is a lot of things to do, right? Around energy generation and storage, around sustainable plastics, around net zero carbon fertilizers, and many classes of problems that, obviously they have a policy part, but they also have a very big materials part, right? Like everything is made of something, and it typically takes 20 years for a new material to make it to market. For the materials that do work out as products, it takes about 2 decades, and somebody thinks of them until they're actual products at scale. And we just cannot afford 20 years to develop some of these new technologies. And an example for something in the future that could be exciting is sodium batteries, right? Like, how do we make batteries out of something that is dirt cheap and not constrained by supply? And it turns out in other places, we've seen technology change the world at the year scale, not at the decade scale. And you can see my examples keep getting older. I change this slide every few weeks, and my examples feel very old. But this DALI is a year and a half ago, right? 2 years ago. So I think, and it's proof of sort of the incredible speed at what artificial intelligence is moving, right? Even regardless of one skepticism about sort of how much artificial general intelligence large language models exhibit, they've definitely shown uncanny performance. I think we can all agree it's uncanny how performant they are. And they're doing tasks that we thought, 5 years ago, we thought were impossible. So how do I get these to invent materials, right? That's sort of the underlying question that I'm trying to weave here. Like, how do we make that type of advances, fast-moving advances predicated on new hardware and new software and lots of data work for for the innovation in the materials space, particularly in energy and sustainability. And I would highlight, and this is important, that when we want to do materials design, we're looking to outperform the best performer ever. So it looks more like Go or chess, right? That we're sort of these very strict rule-based games rather than literature, right? Like, when you look at a large language model today, it writes like a high school student, that has done some Googling. So it's okay, right? It's surprising that a machine can do it, but it's not best than the best human, right? Sentences look cranky or whatever. It's fast. It's incredibly performing, but it's not better than the best humans. However, when we talk about materials or drug discovery, we want to be better than the best ever, right? So it's a slightly different, harder task. And there is another difference, and I think everybody suspects this. We don't have a whole internet of data to train on in the materials space, right? Data is very scarce, very sparse. It's siloed, it's heterogeneous, doesn't have good metadata. Self-supervision doesn't work as well, but we do have the laws of physics on our side, right? For many of the things we're doing, there is this sort of bottom-up way of thinking about them that is fully quantitative, very well understood. It's just expensive to simulate, right? So in many places, we know what the physics are that should matter, and we build our models with sort of whatever amount of physics we can afford, and we typically can be predictive. It's just expensive, right? I'm not talking about black matter, where dark matter and black holes, where maybe the physics are unclear. But for something like conductivity, electrical conductivity, we know the rules. It's just that they're too expensive to simulate by hand. So my group tries to exist in this continuum to see how much of the big data tools we can bring onto the physics to build faster interpolators and sort of make the physics run as fast as we can. With approximations that we are already agreed were acceptable, or to infuse symmetries and invariances and domain-specific adaptations into the neural network architectures, into the machine learning models that we do, right? So this whole spectrum of tasks, and maybe in this community, I can spend a little time here. So sometimes I go faster here, but interatomic potentials can be thought as sort of the cheapest machine learning thing one could do, which is making a surrogate. Is a regression task where we make a surrogate for quantum mechanics that produces energies and forces out of atomic positions, right? This is a very trivial, quote unquote, regression task, right? But we do molecular dynamics to sample the Boltzmann distribution, right? At the end of the day, most of the MD goes into making a hard distribution tractable numerically. So it turns out what we're doing here is sort of some generative task that draws from a hard distribution. We like to think about sort of multi-fidelity models that build up. They get diversity out of simulated data, and they get accuracy out of experimental data. How to make these two work together in transfer learning, or multitask, or multi-fidelity strategies. And then more black boxy, there is ideas around sort of Bayesian optimization, inverse design, particularly in coupling with robotized experimentation. So I'm going to walk through sort of a list of I believe, sort of more mundane to more esoteric applications, but all of them built around auto-differentiation and machine learning. And the first thing I will mention is machine learning potential. So starting from the left in my previous plot. Like I said, we work on atomistics. Other folks have more beautiful differential equations or more complicated differential equations to solve. But at the end of the day, for materials science at the atomic scale, we're mostly just solving Hamiltonian dynamics, right? We're moving our atoms forward following classical mechanics. We need to have this tiny integration time step. And we just sample the universe one femtosecond at a time. Other folks in fluid dynamics, or if you're a mechanical engineer, they get sort of a more complicated set of differential equations to put together. But in our world, the differential equations that we move forward are not that exotic, right? But still, ideally, when we simulate with these techniques, we look at thousands to maybe millions of atoms. But matter is made of 10 to the 20 atoms in sort of at day-to-day scales. We look at 10 to the 20 atoms. So we're taking very small slices of matter, We're integrating time at femtosecond time steps, meaning that we need to call our function, we need to call this function about a billion or a trillion or a quadrillion times, depending on the time scales we want to access. And the biggest supercomputers in the world have been built precisely to just brute force your way to time here. And we need to know the interaction potential that governs, right? There is an interaction potential inside here, this Hamiltonian. So all of these are places where machine learning can help, right? We can try to reduce the amount of matter we look at, and we call that coarse-graining. We can try to skip ahead in time or draw from this complicated distribution in a less sort of auto-regressive way and try to just get good draws without having to propagate forward in time and have sort of such correlated samples. And interatomic potentials are the thing I'm just going to talk about that relate the position of atoms to their energy and the forces acting on them. So I'll start with an example. I'm going to have, I realized, maybe a few examples of batteries that catch fire, but it's a big deal, right? Like batteries are very expensive. They're energy dense. Lithium ion batteries are reasonably energy dense. We can always aspire to do better, but mostly one of the things that complicates the use of batteries at sort of grid scale is the fact that they contain a flammable liquid. So the electrolyte material that mediates the motion of lithium from one side of the battery to the other, at charge and discharge, is a liquid, because only a liquid lets ions move around fast enough. But of course, this liquid is not mechanically stable. So if anybody, for some reason, there is a little puncture in the pouch that contains this liquid, it will squirt out in the presence of highly oxidating lithium and air. It will result in a fire, and then the whole battery stack catches fire. And you've seen sort of every year we see a few of these big scale fires in large battery installations. So there's a lot of appetite to use a solid material instead of this liquid. And the winning solids these days, and since the 80s, unfortunately, look like this. They look like polyethylene oxide. So one of the first questions we asked in our interatomic potential world is, well, okay, let's start with something simple. Let's see what's the best polyether we can make to chelate lithium, right? It's a pretty simple task. It has some chemical space of different ethers, I could imagine, but it's not very sophisticated chemical space. And there's a configurational problem, right? Because I need to figure out the pose where the organic best surrounds the lithium. And then I've got a little bit of a Hamiltonian problem, because classical potentials are not very good at this. Classical potentials think of this as point charges, but of course there is very strong polarization here. So it's a place where DFT does a good job and quantum mechanics does a good job, but classical mechanics doesn't, right? So we propose to do this task of finding one of the best member of this chemical space has the best pose to chelate around lithium with a neural network potential. As we were doing that, maybe I don't have a slide about this, but you've heard about graph neural networks in the past and equivariant graph neural networks. So typically, neural network potentials these days, they can pretty much learn whatever you throw at them. So if you got tens of thousands of data points, you can definitely make of energies and forces at some ground truth level. You can feel a neural network force field that reproduces that training data with sort of kilocal per mole energy accuracy and kilocal per mole per Armstrong force accuracy. That's pretty standard. The question that we encounter, us and everybody else, is generalization, because it turns out holding out test data randomly is typically not enough to measure the performance of force fields. So here, what we encounter is that even though our held out performance was very good, when we started doing dynamics, the error in the energies was sort of an order of magnitude more than it should have been. It was over 10 kilojoules, and the error on the forces was over 10 kilocal, and the error on the forces was over 5 kilocal. So we were sort of almost an order of magnitude off of what the held out performance would have suggested, right? So if we start the simulator, run some simulations, put them back in the Oracle and see how we were doing, turns out the model was extremely overconfident, and actually we're not as good as we thought we were. And the problem here is that the training data, this is a 2D projection of the training data on the phase space of the actual simulator. The training data didn't cover the phase space where the simulator is going to go. And this is a fundamental problem of neural network potentials, that there is typically, by definition, the training data does not cover the full phase space, because if we had the full phase space, we would just do reweighting. We don't need to run molecular dynamics. If we already know the full phase space, we're done. Meaning that we're always going to be in a setting where our surrogate energy model doesn't have access to the full phase space. It's going to explore when you do run the simulation. So here we just added some diversity to make sure that we don't recalculate the same point twice, and slowly through this sort of sequence of generations populated the phase space that the model eventually visits, and finally reach self-consistency, where the model visits the phase space that it was trained on in a self-consistent way, and then we get good performance, and we find some of these molecules that are a little bit than the incumbent. But the take home here was sort of about the brittleness of machine learning potentials. We've gotten better at this, and I will talk a little bit more about differentiable uncertainty in a minute, about some of the tricks we've used to learn more intelligently. But I have another example that is a little bit more recent on ionic transport. It's the same idea. I want a solid that conducts ions, but in this case, it's an inorganic solid. This is LGPS, have existed for a few years. It was first discovered experimentally. And it's a material that conducts ions almost as fast as a liquid. There is sort of channels here. You can see them, all the yellow atoms are, and the green atoms form the inorganic backbone. And then the lithium atoms have channels to circulate from the bottom to the top. So there is a Z channel, and then the crystal is tetragonal. So there is an equivalent X and Y plane. So the lithium ions move around this channel along each of the crystallographic orientations. So again, classical force fields are really bad at this type of chemistry. So people didn't have sort of classical force fields to try. When they did ab initio molecular dynamics, this is the red points. They had to do them at very high temperature, because this is ab initio molecular dynamics, meaning that you're paying the full DFT price to do MD. So you get a budget of about 1 picosecond. So whatever you're looking at needs to happen you need to get good statistics for it in about 1 picosecond. And the only trick they can do is high temperature. So this was 800 Kelvin or higher, right? So they're simulating at these very, very high temperatures. And then these black lines are the experiments where they're simulating, where they're measuring at realistic temperatures. And it turns out the theory and the experiment agreed well on the slope, on the barrier. And this is diffusivity. And this is 1 over temperature, right? So they agreed on the slope, but they don't agree on the intercept, right? There's something off. So here we applied the same trick as before. We fit a neural network potential on data such as this. But since the neural network potential is much faster, we were able to sample at much, much lower temperatures that now start agreeing with experiment. And what we found out, that there is a phase transition. So everybody was right. The theories were right. The methods were correct. The experimentalists were right. But the material was doing what it wanted. And what it wanted is that it has a phase transition at around 500 Kelvin, where the motion on the X-Y plane stops, meaning that the ions stop moving sideways and they can only move sort of in trains forward. And that kills off a bunch of entropy. So you can read this as sort of a bunch of entropy going away. And we were able to see this through ab initio, so molecular dynamics supported on a lithium, on a neural network potential. But again, this requires multiple generations of training data. If you're a little bit more,
ask you a question?
Yeah, go for it.
So what are the sort of the aims for? So what is an aim for this diffusivity? Like, what would be a good value to have? Like you show this curve where you have a nice reproduction of the. You see sort of this phase transition, and you see that you can sort of reconcile these two different regimes of as a temperature dependence. But what would be sort of like, what would the of course lower is better, but what would be sort of like
that's a great question. I think I have this in the wrong units for an intuition. So liquids are a millisiemens per centimeter. So the electrical conductivity in solids, it's easy because all the lithiums move. So transforming this is a diffusivity. Transforming a diffusivity to a conductivity is not a problem for a solid, because all the lithiums move. None of the other ions move because they're in the framework. It's what's called a single ion conductor. So this conversion is easy. In a liquid where an ions move too, diffusivity to conductivity is tricky because you only care about the conductivity for the positives, right? Like the fact if the anions move very fast, that's bad because they're not. You care about the lithium moving. You don't care about the counter ion moving. But typically we look for electrical conductivities of 1 millisiemens per centimeter. So that's what liquids get you today. The best polymer almost gets there at ATC. So you need to run your imagine if it's a car, the engine needs to be at ATC before you actually sort of can run the battery well. So LGPS is very fast. So part of this was trying to understand the mechanism, because LGPS is fast enough, but it's not stable against electrochemically, or not stable enough electrochemically. So it breaks down when you apply enough voltage through it, right? So you start oxidizing the sulfur, right? So it doesn't have good electrochemical stability, but it has very good conductivity. So the question is, how is this channel motion? What can we learn from this motion so we can take it somewhere else? So in terms of, I think this is a reasonable temperatures for us, right? This is about room temperature. So 10 to the 8, 10 to the 7 would be good, right? Like this is a good ballpark. This material is very good at conducting. It's not great. It's not very stable.
Okay, thanks.
Yeah. If you're more on the molecule side, this definitely works for molecules. It works for sort of even pretty sophisticated properties of molecules. We've been interested in excited state force fields for a couple of years now. You can imagine how this is a hard problem, because excited states are sort of very non-local, right? They're a property of the whole molecule, so you need sort of very non-local perception fields, and message passing neural networks do this reasonably enough. So we've studied sort of the process of cis-trans photoisomerization of molecules such as this, such as azobenzene, that goes from trans to cis. And if you've ever had sunglasses that go dark, or regular glasses that go dark when you go outside, it's something like this, right? A molecule is in the ground state, absorbs light, and in the process, once it absorbs light, it's not in a minimum anymore, so it follows the potential energy surface down. And at some point, there is a so-called conical intersection where it can either it falls back to the ground state, and this is close by to the transition state for the isomerization. So it can either fall back to trans, or sort of keep going all the way to cis. This can be simulated. We know the physics. It's just that it's not just quantum mechanical methods that you need to call, it's excited state quantum mechanical methods. So typically this is scaled to like n to the 4th with the number of atoms. It's kind of an order of magnitude or 2 more expensive than ground state quantum, meaning that the acceleration for machine learning is even better, right? If you manage to do this with machine learning, you get to unlock sort of a couple of orders of magnitude extra value. So that's what we did. At the end of the day, what it becomes is a multitask force field that, in addition to predicting energies in the ground state, it needs to predict the energy in the excited state. So it's a multitask force field. We perform a trick here that wasn't invented by us, which is that it turns out it's much easier to learn the so-called diabatic states than the adiabatic states. And you can think about this sort of, learning this very peaky function is way harder than learning these smoother functions, right? So we learn on a basis where the potential in the surface are smooth, and then we perform a change of basis. We diagonalize our states to obtain the adiabatic states, which is what the quantum gives us, right? So we do matching of the quantum, but the internal state that the neural network learns is a much smoother, sort of less jagged function. And again, kilocal per mole, it's always kilocal per mole for the training data, right? For chemistries the model has seen, geometries that are new, but chemistry that it knows, energy of the ground state, energy of the excited state, the difference, the forces, these are the coupling between surfaces that we need for non-adiabatic dynamics. All these things are sort of ballpark 1K cal for seen chemistries, and it even generalizes pretty reasonably to new decorations, right? So we had 8,000 unique isobenzenes, and for substitution patterns that were not in the training data, we still get sort of 3. It's not unbelievable, but we get 3 with 2 and a little bit over 1 for the couplings. So with this, we've been able to screen these guys for redshifted, right? Typically, one of the things that people are excited about photo switching is photopharmacology, having drugs that switch conformational states on demand. So you can imagine how you make a drug it's in an inactive conformer that doesn't do anything, and it just stays. And at some point, you shine light around a lesion or a cancerous tissue or some sort of well spatially and temporally localized area. It changes conformations and it becomes active, right? So typically, in order to do this, you want to have a near IR absorption because the poly is transparent in the IR. And you want to have a molecule that sticks around in this state for as long as it can, or as long as you want. So we also apply this type of force field active learning campaigns to understand the thermal inversion, right? So if I photophysically make cis, is it going to return to trans just by thermal fluctuations? And it turns out, even though they're just thermal fluctuations, it's still an excited state phenomena. And when it's in the cis state and it starts wiggling with temperature, instead of going over the barrier and coming back to the trans, the return from cis to trans, the deactivation of the drag, is actually mediated by intersystem crossing to the triplet. So again, even if this seems just like a thermal process, it turned out to be also an excited state process that requires sort of the full-fledged quantum mechanical ground truth. And where all this comes together, where we've screened the chemical space of photopharmacology, of photo-switchable drugs. So these are all the targets that are in the docstring pipeline that Jose Miguel Hernandez Lobato from Cambridge put together. And we've quantified for these sort of thousands of azobenzenes, what is the difference in binding in docking score between cis and trans. So just try to get a sense for which targets are sensitive to photoactivated drugs and by how much. And I think this was a little bit of cold water dropped on us, because the difference in the score is not huge, right? You can see that most of the time the difference is, maybe a little bit bigger than 0, but it's in the couple of kilocals per mole, right? There's no too many compounds, maybe this one, maybe EGFR. We've been sort of fortunate enough to find a drug. There's some molecule that has a 4 kilocal per mole difference between the cis and the trans, but it's, it's a little bit of a needle in a haystack, even for switchability, which we thought would be a little bit more amenable. But now we're bringing all these pieces together to score molecules on their absorptivity, on their lifetime to switch back and forth, such that we get sort of tunable timescales, and on their ability to bind the biological targets of interest, and see if all these pieces can be brought together to get a sense for a photopharmacology drug space. I'll sort of keep going up in the ratchet, but feel free to ask any questions of my sort of differentiability of things we care about to talk about uncertainty, because I've been a little bit sort of cagey about the ability to quantify uncertainty. Neural networks, like I said, overfit to the space of the training data, and even using test data sort of gives you an overconfident model. There is a few techniques to quantify the uncertainty of neural networks. Typically, the thing that everybody in the field trusts most is ensembling. You just train multiple neural networks with random initial weights and ideally even different architectures. So maybe one more convolution, another one has sort of a narrower latent space. Just mix and match both architectures, random seeds, and data splits, and get sort of a little bit of an ensemble, ideally 5, but maybe 3 if you're a bit cheaper, such that the disagreement between the models in the ensemble can be taken as the variance across the ensemble can be taken as a measure of uncertainty, right? Where for points where all the models agree are typically certain, all the models are giving you the same prediction, and points where they disagree, you can take off as uncertain. There's other techniques. Mean variance estimation works when you have uncertainty in the data, but it's not really that good at quantifying the uncertainty in the model. This is a trick to deal with noisy data, which is not too big of a problem. For the task I just described, the experimental data, quote unquote, has no uncertainty because it's quantum mechanics. If I do quantum mechanics again, I'm going to get the same answer with numerical precision. I'm going to get 10 to the minus 7 Hartree difference if I run DFT again on the same molecule. So I don't have aleatoric uncertainty. This is not a problem. And then Fox, a couple of years back, proposed, and maybe Rocio has been close to this back in the day, evidential regression, which sort of combines the ability of mean variance estimation to quantify aleatoric uncertainty with a distribution over Gaussians, such that the mean and the variance that you learn in mean variance estimation are themselves also Bayesian. And you can sort of make a hierarchy of draw from a distribution that parameterizes distributions and capture both the model's own uncertainty and the data's own uncertainty with mean variance estimation. And then recently, some folks have proposed sort of latent space distances. As you know, there's a couple of efforts around quantifying uncertainty just as sort of distance in embedding space. And all of these techniques have something in common, and they're the fact that they're written in the same auto-differentiable code as the neural network. So it turns out all of these are differentiable themselves, right? The way we measure uncertainty is also a differentiable function, right? I can take the derivative of uncertainty with respect to the input parameters, right? Just like when I calculate forces, I take the derivative of the energy with respect to atomic positions. If I define my uncertainty as the variance of the forces, this operation is differentiable too. So if I just take the gradient of these with respect to the atomic positions, I literally have the uncertainty force or the uncertainty gradient, right? I've got an arrow that points the system to high uncertainty regions. So I don't need to wait for the model to bump into uncertain regions, right? I have an arrow now that points the model towards the places where it's uncertain about. People do this. This is called adversarial training or adversarial attacks on other classes of models, where it's using the model's own sort of undecisiveness to point it in the right direction. And in our case, we've used it as an active learning technique, right? So now we've got a gradient for uncertainty, and we'll just move the atoms in the direction that maximizes uncertainty so we can gather those points. And if folks are alert, they will quickly think that, yeah, that will point to a plasma where all the atoms are flying around and I get some ridiculous configuration that makes no sense. And that is correct. We need to reweight everything by its likelihood, right? And of course, we already have a bunch of training data. So we already have an ensemble to make up this sort of pseudo partition function or this denominator of all the states the system could be at. And we've got a neural network that predicts energies, meaning that we can score any new framework based on its energy and thus based on its likelihood. And these two things put together give me this sort of likelihood weighted uncertainty. And then when I take the gradient of this, I take steps both in likelihood and in uncertainty at the same time and try to maximize uncertainty and maximize likelihood at the same time. And this is something that we use routinely for all those, some of the results I showed you were already utilizing this idea. This is an example from a 2D well where we start with empty data in one well. So the model has no idea there is a second well. And this is where the local maxima and uncertainty are, the black points, right? So we start from the white points. We do gradient ascent over uncertainty. Of course, you know, the model is uncertain in sort of a stochastic way. So it lands at these 3 local points in the first generation. And as we do more generations of gradient ascent, it quickly identifies and traces the boundary of that second of the second well. And in our experiments, this is more data efficient than random, and better at random at finding low energy, i.e. high likelihood frames. So we typically do this now. Folks have proposed to do enhanced sampling with uncertainty as a collective variable, which is not unrelated. That's a similar theme. And in general, to be intelligent about finding the points that you need, rather than just running MD and waiting until you bump into uncertain regions, because that means that you need to do the production run a bunch of times until it stops finding places where it breaks. Rui, the same person that invented the previous thing, has sort of been trying to see which of these uncertainty measures are good or better for this. So we haven't published this yet, it's coming. But it turns out the only thing that we believe can be trusted is ensemble uncertainty. It's not amazing. So I think if you're starting your PhD and you want to think about uncertainty, it's very much an unsolved problem. Ensemble is the one that gets us sort of the fewest catastrophic breaks. But you can see how evidential uncertainty, which I said, you know, it's good because it captures aleatoric and epistemic uncertainty at the same time. But this is such a weird plot. So this is the difference between what the variance in the force and the error in the force. And we get this sort of this bimodal distribution that doesn't make a whole lot of sense, right? So there's sort of high error, low uncertainty points, and then there's equally high error, way higher uncertainty points. So we're still sort of trying to figure out what's best. But the most robust choice, if you're not going to do research on this and you're just going to do research using this, my instinct would be to recommend you do ensemble uncertainty. And my last sort of broader comment about force fields before I move on to even fancier differentiation is that forces are not enough, right? Like I've tried to make the argument that especially forces on a held out subset of points you have at the beginning, it's not a good measure of what the force field is going to do, right? Because force fields are supposed to be these stable functions that will work when you find rare events. The whole reason we do MD is to find the rare events that we cannot sort of, just wait for them to occur, meaning that they're not going to be represented in the training data, right? There is something sort of almost tautological about creating the force fields, because they need to be robust for the rare events when they come up, but you don't really have them in the training data, because if you did, you would not be doing MD in the first place. So Qianfu here sort of made this argument very well in this preprint last year. And we're hoping that the reviewers will think that this is machine learning, because we definitely think it is, but there's always one reviewer that doesn't. But in general, the way you evaluate a force field is testing it in the task that you actually want it for. And the task is not reproducing forces. The task is running molecular dynamics. So if your MD is for structure, you need to check if the RDF, if the radial distribution makes sense, right? If you want to look at kinetic properties, well, then maybe also make sure that you get stable dynamics over long periods of time, and so on and so forth. And sort of maybe ratcheting things up a little bit more.
So Rafa, can I ask you before you continue this? So I think it's a sort of, maybe you can comment, maybe it's something we can keep a bit towards the end, but it's there's been a bunch of these data sets that have been, so QM9 and so on, there's a bunch of data sets that are out there that are used as sort of like ground truths, and there's a zoo of, as you also talked about, different neural network potential models where people are trying to squeeze out. So I think the point in this preprint that you highlight is that this is not sort of the whole story, but I mean the task of estimating or approximating classical or force field is not new, right? You mentioned in the beginning of your talk that the sort of interatomic potentials and sort of classical approximations of quantum mechanics it's been around for a long time. And the way that data acquisition has been done, or data generation has been done to train those potential has been a lot more systematic than just like building a bunch of molecules, minimizing their energy, and then like pumping out some observables, right? There's been a lot of thought going into this. So do you think that there's something that the machine learning community, or sort of the machine learning potential community, can learn from this way of generating the data for training? I mean, it seems like that this is maybe one of the missing links.
Yeah. So I mean, at the risk of derailing my own talk, I can say, so yes, I agree with almost everything you've said. We've personally, for instance, in the group, we have tried to learn classical potentials end to end. So the same way we train a neural network, we take the same data and we train a classical potential, right? And we see that OPLS, class 1 force fields, typically get you 5 to 6 kilocals per mole per Armstrong, but of course they cannot blow up by definition. Class 2 force fields are almost impossible to fit end to end. They're extremely degenerate, and all the parameters sort of move each other's gradients. So it turns out class 2 force fields kind of work because they're held together with pins and chewing gum, because they're extremely degenerate, and the quartic term could eat up into the square term, and it's been really hard to learn anything better than OPLS end to end. So another thing we've learned is that you need torsional scans. I think this whole community has tried to say, well, I'll show it an ensemble of data and I learn the distribution. Is like, no, you need torsional scans. I've wasted a lot of our own cycles trying to not do torsional scans by brute force, but it's really hard to learn torsions without torsional scans. So, and people knew this, and we've kind of tried to, we'll do MD, and from the MD learn the parameters. Like, no, like MD17, if you, maybe MD17 is, they're very small molecules, very rigid, very thoroughly sampled, so it's not maybe a great example. But in general, training on molecular dynamic short trajectories doesn't produce enough torsional data to make good torsions. So one is torsional scans. And then there is another bucket of things, which is long range. All these models are sort of relatively myopic. Some of them are extremely myopic, like sort of Allegro, right? It's very local. It's like literally 6 Armstrong, right? Something is 6.1 Armstrong away, you won't even see it. But even, you know, the message passing architectures, they get long range effects by averaging and in sort of a messy way. So electrostatics and polarizability, we need sort of a classical, well-structured electrostatic way to think about. I think it needs to be polarizability. So I think it's not just enough to learn point charges. We need to learn a little bit more. So I don't know, like amoeba, neural network amoeba with any, that type of thing, I think it's completely necessary to be realistic, right? Because A, we're myopic, and B, we're sort of trying to learn everything from an ensemble. And my last point, and maybe this I can hook up with this theme, is learning from observables, because it turns out the classical force fields are parameterized a lot from experiment densities, just starting with the densities, right? For Lennard-Jones parameters. If you try to fit Lennard-Jones and dispersion parameters from the bottom up, again, it's really hard. It's very, very unsensitive, right? So a tiny change in the Lennard-Jones, this doesn't do anything to the density, but it makes a very different simulator. So one set of tools that would allow one to fit from observables is differentiable MD. And this builds up on seminal work by David Dubeno. I think this was the best paper in NeurIPS in 2019, or this is the second one. The first one is earlier, which is the idea that one can utilize neural ordinary differential equations to back propagate through a molecular dynamic simulation. At the end of the day, right, like I said, we're solving this lousy quote unquote differential equation, and there is this thing called the adjoint trick that the engineering community has also been using, which is just the definition of sort of the instantaneous loss. So this would be the whatever loss function you're using, what is the derivative of that loss with respect to the instantaneous state of the simulation in P and in Q, right? In momentum and in coordinate space. And it turns out by integrating this adjoint backwards in time, we can take the derivative of a loss with respect to parameters, be it parameters of the simulation or parameters of the initialization of the simulation by integrating the forward trajectory backwards in time. And by integrating, I just mean adding. So you add up all the adjoints as you unroll the molecular dynamics trajectory backwards. And it is possible to define a gradient-based loss with respect to simulation parameters. So for instance, this is if my pointer will work, this is a molecular dynamics trajectory of a chain of beads that we ask by gradient descent to adopt a helical structure, right? So we say, what is the neural network potential whose interactions make a chain of beads become a helix, right? So this is the equilibrium state of this helix. It's not frozen, right? It is oscillating at a certain temperature, and it's oscillating according to the potential dictated by the gradient descent that optimizes some reward function based on the structure. So this takes me to the point which is mentioned, Simon, which is fitting from observables, right? And this is something that the interatomic potential community has been doing forever, which is knowing what the experimental answer is supposed to be and fit into that. So it is possible to do this end-to-end. So this is water, and we're fitting the radial distribution function of water end-to-end. So again, initialize a box with a bunch of beads, simulating them forward according to molecular dynamics at a certain temperature, being the distances into a differentiable radial distribution function, compared with experimental value, and back propagate to the neural network, to the interatomic potential, such that we find an interatomic potential whose equilibrium state is the RDF that we want. And you can see how it works for sort of the various pairwise atomic interactions in water. This is kind of the same idea with Wuji here in this 2022 paper, dove a little bit deeper into this, and for instance, added temperature as a variable to fit a temperature-dependent coarse-grained potential, such that the same potential takes temperature as a variable. but reproduces experimental observations at different temperatures, right? So this is a coarse-grained potential of water. It only tracks the oxygen and reproduces the radial distribution function of oxygens at low temperature, mid temperatures and past boiling simultaneously. And you can see how we get sort of this smooth, well-behaved potential, pairwise potential, CG potential, as a function of temperature explicitly. And something else that we probe, there is something that you may have heard that's called Henderson theory from liquid theory that says that one pair potential has one radial distribution function. There is a bijective relationship between pair potential and radial distribution function. And this is true proof-wise, but it's not practically helpful. And you can see here, so we're doing our differentiable simulation trick on this high-density Lennard-Jones fluid. We train a potential either by our technique or iterative Boltzmann inversion, and then we compare the RDF that we got with the training RDF, and they look very, very, very similar. There might be some discrepancies in the tail but numerically, this seems good enough. And look at all the blue lines are different unique solutions that we got from the gradient descent approach. So it turns out there's a gazillion pairwise potentials, all of which give you essentially the same RDF numerically, right? They're not sort of to infinite precision, they're different, right? But to numerical precision, all these RDFs are the same, but all these potentials are very different, right? Some of them have a maxima. All these pair potentials, we're trying to reproduce Lennard-Jones, right? It's there in red. So we're trying to reproduce Lennard-Jones end-to-end, and we end up with sort of whatever, tens of different solutions. Some of them have a maxima, some of them don't. IBI, iterative Boltzmann dispersion, is not perfect either, but we believe this is particularly salient with end-to-end learning. Sorry, I skip one slide. There is one more thing we've done recently, and this I think it's maybe going to get accepted into ICLR, maybe not, we'll see. And it's this idea of using differentiable simulations to cross barriers. And the theme here would be, for processes for which I know the reactants and the products. So maybe, protein folding might not be a great example. If you don't know sort of what the fold is that's going to show up, right? That's more unsupervised. But in chemical reactions, we typically have a good, oftentimes people know what the products are. And it's just what was the mechanism, right, by which this catalyst made this product, or why was it the composition that made sort of this molecule go? So we've taken a stab at this, thinking about sort of reactions that start from a basin and end up in another basin. So we know where these two guys are, and we want to, as fast as possible, get sort of a good estimate of what this path, what the path is, right, what the collective variable is that expresses this transition, and what the free energy profile across this barrier is. And it turns out this can be done with diffsim by having sort of the two ends pull each other, right? We put some loss function that rewards crossing over, rewards reactant crossing over into products, and rewards products crossing over to reactants, and we just sort of crank up that a biasing potential that rewards the dynamics being sort of crossing back and forth as much as we can. So this is sort of a collective variable free way to think about this, right? We only need to know if I made it. The only thing I need to define is a binary success metric. It's like, did I make it into the products or not? And if I did, then I have enough, I look at the end of the simulation, and if at the end of the simulation I have crossed, then the model works, and if I haven't, I get a gradient to get as close as I can. So you can see how the loss goes down, starts high and goes down. This is the number of trajectories in this 2D potential that cross. This is a collective variable that can be learned after the experiments, right? After we run the simulation, we've crossed a bunch of times. So now we have sort of good statistics for inferring a collective variable. And this is what the original potential of mean force look like. And this is what it looks with the biasing potential. So it's still not perfectly flat, right? It's not perfectly converged, but it's pretty close to converge, and has given us a very good collective variable. So once you're here, you can do a little bit of metadynamics, right? Or a little bit of adaptive biasing force and finish it off, because you already have sort of a fairly diffusive landscape and a collective variable, right? Which we necessarily didn't have a priori. I don't have a lot of time, so I would just say we had to do some things here in particular, because molecular dynamics is chaotic. We had to do Langevin integration to make sure that the system doesn't keep sort of some insane memory of far ago steps. So we need to do Langevin dynamics to sort of avoid exploding or vanishing gradients. And then we found this interesting, which is we need to do partial backprop only to avoid sort of having, because P and Q are nested, right? These derivatives are nested. So my current P depends on my prior Q, and we want to decouple that such that our systems, our biasing potential only depends on Q, right? But it should be non-Markovian. Our biasing potential shouldn't depend on the velocity of the particle. It should only depend on the position of the particles. So we need to sort of take a quick trick inside the neural network. You know, this works for 5-dimensional potential. This is how the profile looked like in the toy model. This is what it looks after differentiable MD. Again, it's not fully converged, but it's converged enough that we're seeing crossing and it keeping a collective variable. So it's done sort of autonomously most of the hard job, and it's just a matter of finishing it off. And this is the same for adenine dipeptide. So you can see how it's found sort of, you know, going from here to here. It can go over periodic boundary conditions, right? Or it can shoot sort of 2 paths around the barrier. And essentially found sort of a few channels autonomously that get it from one side to the other. And you know, if people have questions, I can stop here, or I can talk a little bit about the coarse graining. So your folks' choice.
We have a few questions in the chat, so maybe you can address them.
Oh yeah, let's go. Sorry, I lost the chat.
David and Rocio have questions.
Oh, I apologize. I was like, I'm gonna keep looking at the chat, and then I stopped. Let's look at, on slide 20, adversarial uncertainty in higher dimensional spaces. Yeah. We've done it with, so yeah, we do it with our force field. So we do adversarial attacks on our force fields all the time now. It's sort of, we start whatever way we can with some like ultra high temperature MD or somebody else's force field. By now there is enough pre-trained force fields out there in materials especially, and you know, at least they don't explode. They may not be great, but at least they don't explode. So they produce sort of sensible frames at relatively fast. And then we start off from there and we do adversarial attack all the time. We also do attribution. So it's the same idea, but locally. So when you have a really big box, you can do attribution. It's the same derivative. But then look at the atoms that have very high uncertainty gradient. Rather than just distorting and following the uncertainty gradient, we use it as a warning system. And if some atom is on the verge of high uncertainty, that's how people do attribution, or one of the ways to do attribution in neural networks. We can also utilize to carve out parts of the system that are uncertain. Sometimes when simulations are very large, we can't really go to the oracle. I mean, mind you, doing this with a metalloprotein, you're not going to throw in the whole metalloprotein to the oracle, right? You need to carve out what region is uncertain and just relabel that region with the oracle. So yeah, we do this in, you know, for LGPS, right? It's a 4x4x4. This thing was a 4x4 supercell, 4x4x4 supercell with 50 atoms in each primitive. So it's like a 4,000 atoms, and we do adversarial attacks on things of that size. And then feed potential with diffnd, how much? I think about 1,000 atoms. It's still sort of doable. We haven't pushed it farther than 1,000 atoms. So I don't know if it's going to be enough for protein folding. I would say if you're going to do anything protein related, we would do it with CG proteins. We would feed, so you could think of 1,000 amino acids whose geometry goes to a reasonable place. And then Luigi for uncertainty. Yeah, we do ensembling over everything we can. So the question is whether we do ensembling only over weights or also over data folds. So I was going fast, but we try to do ensembles over weights, over initial weights, over data folds, doing something like boosting, right? Sort of old school fold stuff, and over neural network parameters. So imagine, right? If you're doing message passing, for one, you take 3 convolutions, another member of the ensemble has 4 convolutions, another one has 5, and try to make a not only data diverse, but structurally diverse, architecturally diverse ensemble to make sure that we really get good variance. I think if neural network is typically sort of not well calibrated, neural network uncertainty is typically not too well calibrated. So it's still overconfident. Even when you do all these things, the neural network uncertainty is a little bit overconfident. So the more you can do to really throw it off is helpful.
Yeah, I think we can continue a bit. How long do you think that this part is?
Yeah, maybe I'll just say, there is another way to differentiate around sort of the scale of the simulation, which is treating coarse graining as a learnable problem. So coarse graining is this idea of learning ideally multiple things at the same time. One being which atoms become bits in order to propagate fewer bits. Learn the interaction potential of the bits such that the behavior of the bits reproduces the statistics of the all atom system, and learn how to get your atoms back in case you need them. So all these things can be done end-to-end through differentiation. And originally we tried to do them all at the same time, and it was overly aggressive, but I think it demonstrated that all the pieces could be put together at play at the same time. Other people have done this very well, including Simon, of course. He's been in many works that learn what is the best interaction potential for in coarse grain, and Clementi and Frank Noe have, for instance, I really like the recent preprint on. It turns out the way we do these linear operations, right? So we have a linear transformation that sends atoms to bits, and then we have the derivative of the potential in all atom, right? So this is the coarse grain of the forces, and this is the derivative of the CG potential. It turns out this choice of V can be made variationally too, which is something recent that I found very compelling. But in general, all these tasks, compressing, decompressing, and learning the force field or the interaction potential in CG, are all learnable, and they can be sort of set up in this way. So these are examples of learning which atoms belong to which bit, which is somewhat trivial for something like these three phenyls together, right? All the atoms should belong, ideally, all the carbons would belong to the bit according to what ring they belong to. This is a very long polymer where sort of some chunks of the polymer that are more correlated on the center, they go together, and the edges sort of make fewer bits. And what's new that we've sort of gotten excited about in the last year is the back mapping. So our first attempt at back mapping was a linear transformation, which wasn't sort of expressive enough. This is from last year. This is an equivariant generative decoder that we tested on protein structures, and I'll just quickly summarize that. It kind of worked, and it was able to reconstruct the alanine dipeptide from 3 bits. Once you have 5 or 6 bits, of course, you get perfect reconstruction because it's the full information. But for something like signaling, it could reconstruct the conformations of signaling from as few as 10 bits with fairly good reconstruction. And then after doing that, and this is under review now, this, oops, it's taking a while to load. This next paper, Gen Z prot for Z stands for internal coordinates. It builds up on the same theme as before, recovering all atom structure of the side chains of proteins from the CG structure of the full protein in a more generalizable way. So this one now generalizes over proteins. So in principle, it's not system specific. Any amino acid, we've seen enough sort of chemical space across training data that it generalizes to unseen proteins. And then we've expressed the reconstruction task in internal coordinates to avoid bad reconstructions that look okay geometrically, but are not realistic, and sort of really engineer the laws to do all the things that we care about, including, for instance, avoiding steric clashes. We really don't want atoms overlapping, and we need to put that into our reward, or reconstructing sort of both Cartesian geometry of adjacent side chains and the local structure of each side chain. So I'll just leave you with a big shout out to the team, and thank you all so much for listening.
Thanks for excellent talk, Rafa. Really extensive amounts of works and across multiple different directions. Really impressive that you managed to do so significant work across many different sort of subdisciplines. I really enjoyed the talk. So you talked a bit about this differentiable simulator. I think I have a bit of a so the neural ODE formulation is specifically, I mean, as it says, ODE. It holds for the ODE case, but you don't really have an ODE, do you? So these tricks that you were talking about by decoupling the momenta, somehow making a Brownian dynamics of an overdamped approximation when you're doing the training. Is that correct? And then sort of doing a sort of removing the stochastic element. It seems like you need to do this in order for this to work, right?
Yes, that's so I think, yeah, that's I think I agree with you. There have been machine learning community-oriented papers around neural PDEs. So I think folks are, the computer scientists are thinking about it. At the end of the day, you end up with sort of about the stochastic PDEs. So I think that the theory is sort of slowly moving forward. But I agree with you. I think we wrote the reason why we had to drop those cross terms is because it wasn't really sort of a neural ODE. So I think the original formulation and sort of the applications that we're doing have diverged a little bit. That's a fair comment. And for instance, we've seen that because of that, sort of the depth of simulation we can go into, some 1,000 times steps, 5,000, 4,000, 10,000, right? But you can't really backpropagate your way through a microsecond simulation. Even if so you could afford it, all your signals are sort of muddled and you don't really get gradients, or in our experience you get, right? Like but at least they die off smoothly rather than sort of those wild oscillations that we were seeing at the beginning.
So presumably you also have some limitations in terms of defining force fields that will have certain kinetic constraints, right? That you will not be able to have barriers that are higher than a certain thing, right? So you will. Yeah. Is that right?
Yeah, I mean, your biasing potential, this is the thing. Typically, I think we found what we end up learning is as a neural network is some neural network biasing potential such that the behavior is what we want, right? So I think the Erling falls upon a biasing potential. And then if you bias strong enough, you can overcome any barrier, right? So the problem is, do you get to cross that barrier in 5,000 steps at the beginning? Because if you don't, you get no gradient back, right? So that's right. Kind of the trade-off. Like you need to be able to cross sometimes, so you get a gradient to cross more, and then it's solvable. But if the event doesn't even show up, you don't get sort of signal to go search for it. Yeah.
Okay, cool. I think Roshu has a question as well.
Hey, yes, thanks again for the really nice talk. I guess my question is related to the last few projects you showed. It seems to me like you have everything in place to do de novo drug design using the differential MD and then the coarse graining, protein autoencoder, right? Because you can first learn a potential, let's say, that stabilizes a specific protein structure, and then map from that potential to various potential small molecules that would stabilize it. So have you looked into doing that yet?
Yeah, I mean, so I would say I think Sujun, the student, she's in that space. I think we're fortunate not to have tried because Tommy Yakola's diff doc would have smoked us. So it's good that we waited. And we're excited to work with Yakola. Sujun is collaborating with his team. I think the tools are there. We try to be sort of find places where we don't sort of need to go toe to toe with computer scientists, and typically that means it's places where the task is not well defined, right? So part of our job is define the task and define a model that kind of does the task. If the task is completely defined and the data set exists, then I think there's a lot of people that are doing such a great job at that we feel it's not a place where we create a lot of value. But yes, I think, I would say my dream task that does what you just said has been in catalysis. So finding what is the chemical environment that stabilizes a transition state. It's completely analogous, right? Like I think that the model that does what you said is the model that does what I said. But that's a place where I think there is fewer push from the community. But somehow we need to make a lot of ammonia So it's like, how do I engineer a polymer that will fold into the geometry that stabilizes this metal organic complex, right? So I would say my pipe dream is more on that side of the, but yes, it's the same task, right? How do I make a polymer fold into the right geometry that I want? Yeah, yeah. It's very inspiring.
All right, so thank you, Rafa. I don't think we have any further questions from the chat. Yeah, thank you again for this wonderful talk, and I'll stop the recording here.
Thanks very much, folks. And if anybody like realizes that, you know, I missed a sign or something, or just have a question, just send me an email. I'm happy to chat with folks. Thank you very much for having me.